Hi guys, in this video what we're going to look at is what's called a geometric sequence or series, and it's a sequence such as 3, 12, 48, as you can see here. Hopefully you can see what's going on, that what we are doing is we're multiplying to get from one term to the other. So 3 times 4 is 12, 12 times 4 is 48, and the next one will be 48 times 4. So what we can say here, the definition of a geometric sequence, if we have term 1, term 2, term 3, if we can show that the term over the previous term is equal to a constant, then what we have is a geometric sequence. Okay, so to give you an example here, so we look at the 3, the 12, the 48, so 3, 12, 48. What we have here is T1, T2, T3. If we can show that T2 over T1 is equal to T3 over T2 here, then we can prove that this, or we can verify actually that this is a geometric sequence. So for example, you can see here that T2 is 12 over 3. If that's equal to T3, which is 48 over 12, then what we have here is a geometric sequence. 12 divided by 3 is 4, and 48 divided by 12 is 4, i.e. it's a constant. Now we're going to use this idea of a definition of Tn over Tn minus 1 is equal to a constant in the next slide. So it says here, show that the sequence given by the formula Tn is equal to 3 multiplied by 2 to the power of n minus 2 is geometric. Remember from the other slide what we said was that Tn plus 1 over Tn must be equal to a constant. Okay, so some constant k. So we need to know what Tn is and Tn plus 1. Well, Tn is just the one in the question, so Tn is equal to 3 multiplied by 2 to the n minus 2. And to work out Tn plus 1, it's just using our function laws. So wherever I see an n in this original function here, I'm going to replace it with an n plus 1. So what I now have is Tn plus 1 is equal to 3 to the bracket there, 2 to the power of, I'm going to replace wherever I see an n, I'm going to stick n plus 1, so this n now becomes n plus 1. I'll stick it in the bracket so you can see it. So it's n plus 1, and don't forget the minus 2 here. And we're just going to tidy that up a bit. We're going to t to the n plus 1 is equal to 3 lots of, and it's going to be 2 to the power of n plus 1 minus 2, and that's going to be the same as n minus 1. So just to show you what I did there, 2 to the power of n plus 1 minus 2, the n is just an n. We've got plus 1 minus 2, 1 minus 2 is minus 1. We're now going to see if we stick this on top of each other, or this here, this on top of this one, will it collapse down into a constant? So we've got t to the n plus 1 over t to the n should be equal to some constant. Let's see if that actually works. T to the n plus 1 is 3 to the power of 2n minus 1 over t to the n, which is 3 to the power of 2n minus 2. Okay, so 2 to the power of 2n minus 2. And hopefully you see straight away that these 3's will cancel. Okay, 3 both top and bottom. And what we need to do here is we need to use our index laws. So these are both base 2. So that means this is going to collapse to 2 to the power of n minus 1 minus this on the bottom here. So we're going to end up with, that's equal to 2 to the n minus 1 minus, don't forget your bracket, n minus 2. Okay, then what we're going to do is we're just going to work that out. So that's now going to be equal to 2 to the n minus 1, get that bracket out, minus n plus 2 because of the double negative. And then if you look here, this n and this minus n will disappear. And we've got minus 1 plus 2, which is equal to 2 to the power of 1, which is obviously equal to 2. And 2 is a constant. So therefore, we can say that this now is a geometric sequence. So it then says find the first term and the common ratio. Okay, so the first term, we're just going to stick 1 in. Term 1 is equal to, and we've got 3 by 2 to the power of 1 minus 2. Okay, so just wherever I see an n, I'm just going to replace it with a 1. That's what I've done here, 1, and then that becomes equal to 1 there, which means that term 1 is equal to 3 to the power 2 to the power of minus 1, and t1 is equal to, well, 2 to the power of minus 1 means it's going to be equal to a half, because 2 to the minus 1 is equal to a half, 1 over 2 to the 1. So that's going to be 3 times a half, which is 3 over 2. We've already worked out what the constant is, so we don't have to worry about that. So that's my equal to my A. The common ratio, which we're going to call R, is going to be equal to 2. We've already worked that out over here. But if we hadn't done that, we could work it out by working out T2. So if we work out T2 is going to be equal to 2 to the power of 2 minus 2, okay, which is equal to 3 multiplied by 2 to the power of 0, and any number to the power of 0 is 1, so that's equal to 3, so that means that T2 is equal to 3. And the common ratio is equal to T2 over T1. Remember, it's the n plus 1 over n, okay, so from here, the n plus 1 over n. So if we put the numbers in here, we get, the particular ones we got 3 divided by 3 over 2. And if you do 3 divided by 3 over 2 in your calculator, you'll end up with R equal to 2 as before. So just like before with the arithmetic sequences and series, we can work out the general term, and we can also work out the summation. So we're going to look at the general term on this slide, and you can see here what we're going to try and prove is the general term Tn is equal to AR to the n minus 1, where A is the first term and R is its common ratio. So I'm going to do it with some numbers first. So I'm going to just give you a very, very basic one. So we'll have 2, 6, 18, 54, and hopefully you can see what's going on here. So my A is obviously equal to 2 here, and my R is equal to 3. We are essentially multiplying by 3 each time. Okay, so we can see here my term 1 is equal to 2. Nice and straightforward. My term 2 is equal to, and it's 6, which is 2 times 3. Okay, so it's basically my A times my R. My term 3 is equal to 2 times 3, that's term 2, so here's my term 2 from before. What I'm doing for the third term is I'm multiplying it again by 3. And T4, for the last one, I'm taking the third term, which is the one above it, which is 2 times 3 times 3. So I've got 2 times 3 times 3, and then I'm going to multiply that again by 3. Now, hopefully, you might spot a pattern here. So you can see here that term 1 is just equal to 2. And in the general case then, if we have term 1 over here, term 1 is equal to my first one, which is A, which in this particular one, if you look at the numbers, is 2. Right, okay, term 2 is equal to 2 times 3. I'm going to leave it like 2 times 3 because it's going to be important that we leave it of this form. And you can see here that this here is A and this here is R. So T2 is equal to A by R. Now let's look at T3. T3 is equal to 2, I'm just going back here, 2 times 3 times 3. Well, 3 times 3 is the same as 3 squared. So what I can write for this one is it's 2 times 3 squared. And notice again, this is my A and this is my R. So if I'm looking for a general formula, you can see that T3 is equal to AR squared. T4, likewise, if you look here, we have A by R by R by R. R by R by R is R cubed, so I'm going to get A by R cubed. So T4 now is going to be A by R cubed. Now hopefully you can spot a pattern here that if you look at this, we've got T1 is equal to A, T2 is equal to AR, T3 is equal to AR squared, T4 is equal to AR cubed, T5, hopefully you've got this, is going to be equal to AR to the power of 4. Can you see where the pattern's coming from? And what I want to work out what the Tn is. And Tn is going to be equal to AR to the power of something. And now let's see if we can spot the relationship. So when n is equal to 2 here, this is 1. When n is equal to 3 here, this is 2. When n is equal to 4, the index is 3. Can you notice, or hopefully you'll notice, that whatever the n is here, the index over the r, the power, is always 1 less. So we can write that as n minus 1, and we now have the proof of a general term or a geometric sequence or series. So let's have a look at this question. It says find the value of the 7th term. So we want to find T7. And we are told that 6 is its third term, so we know T3 is equal to 6. And we're told that 1458 is its 8th term, so T8 is equal to 1458. Okay, the rule that we're going to use is the Tn is equal to ARn minus 1, which is what we just proved in the previous slide. So you can see, let's have a look at T3 is equal to 6. So we can say, just put n is equal to 3 into this formula, and we can set it equal to 6. We know what the answer is. So we have 6 is equal to A, which we don't know, R, which we don't know, and then what we have then is n minus 1. Well, this is 3. This is term 3, so this is going to be squared. Okay, so 6 is equal to AR squared. For T8, we're going to do exactly the same thing. We know that 1458, again, stick it through this formula. A, we do not know yet, so that's equal to A. And then we need to find our R, which is just R. And what we then have is n minus 1, and we have T8. So sticking it into here, 8 minus 1 is 7. Okay, so you can see here that we have 2 equations with 2 unknowns. And what we can do here is rearrange one and put it into the other. So you can see we have A in both of these. So what I'm going to do is I'm going to rearrange A is equal to into this equation here, and then I'm going to put or substitute in that A into this equation over here. So I can divide both sides by r squared to get A is equal to 6 over r squared. And then using that substitution, I'm going to put that into there and substitute this in. So I end up with 1458 is equal to A, which is this thing here, so 6 over r squared. Okay, and then to the power of r to the 7 here. Okay, so just do it again. So the A comes in and replaces the A here. So 1458 is equal to A, which is 6 over r squared, multiplied by r to the power of 7. Once we do that, we're going to use our laws of indices. So 1458 is equal to, and we now have 6 multiplied by r to the 7 over r to the 2 there, or r squared. Using the power or our laws of indices, that means we now have 1458 is equal to 6 to the power of r of 7 minus 2, which is 5. We can then divide both sides by 6, so r to the 5 is equal to 243. And then to get rid of the power of 5, we need to take the fifth root, so r is equal to the fifth root of 243, and r is equal to, just stick it into your calculator, you get 3. Now we've got r, we now need to find the a, so we can stick it into one of the formula. The easiest one to stick it in is this one here. So I'm just going to go up to the right hand side here. So we now know that a is equal to 6 over r squared, and our r is 3, so 6 over 3 squared. That means that a is equal to 6 over 9, so a is equal to 2/3. Perfect. I haven't answered the question because we were asked to find T7, but we now have our a and our r, so we should be okay. So T7 is equal to a r to the power of 6. We're going to stick our a in, we're going to stick our r in, and we'll see what the answer is going to be. So t to the 7 is equal to a, which is 2/3, multiplied by 3 to the power of 6. Stick that in your calculator, guys, and you get T7 is equal to, and it's going to be 486. Okay, just like we did for arithmetic then, we're going to be working out the sum of the first n terms of a geometric instead of an arithmetic, and it's given by the formula there. S of n is equal to a 1 minus r to the n over 1 minus r, where r is not equal to 1, because otherwise you'd obviously get a division by 0. Okay, so let's see how we're going to prove this. So we're going to write down our Sn like we did before. So hopefully you can see S of n here is equal to our first term, which is a, plus our second term, which is ar, plus our third term, which is ar squared, plus, and that's going to go all the way to the penultimate term, which is ar to the n minus 2, plus ar to the n minus 1. Remember that Tn is equal to ar to the n minus 1. That's what we proved earlier. Okay, last time what we did was we wrote down Sn again, and we just flipped the order. We put this over here, this underneath here, this underneath here, and this underneath here. We did that for the arithmetic. We're not going to do that this time. We're going to just use another technique here. And what we're going to do is we're going to multiply everything in this equation by r. Okay, so everything in this equation is going to be multiplied by r, and I'm just going to write that underneath, and I'm just going to shift it slightly so you can see what's going to happen. So I multiply this by r, so this here gets multiplied by r, so I get r sine, r S of n, sorry, that's equal to, now if I multiply this by r, I'm going to get ar, and I'm just going to move everything just to the side, so that's my ar. If I multiply this by r, I get ar by r, which is ar squared, so that becomes, that's just going to shift across to this one over here, so that becomes plus ar squared. This one here is going to shift across to become ar cubed. Hopefully you'll see that this one's going to shift across. Instead of ar n minus 2, it's going to be ar to the n minus 1. That means that this one here is going to shift across to be ar to the n, because if we do n minus 1 plus 1, the minus 1 and the plus 1 cancel. So just to say what I've done here, I've got S of n, and that's just equal to a term 1 plus ar, which is term 2, plus ar squared, term 3, etc. And that's gone all the way up to the nth term here. And for the one below, all I've done is I've just multiplied this whole line by r, and you can see here Sn by r is rsn, a by r is ar by r is ar squared. So you'll notice it's just shifting across here. Okay. So the next thing I'm going to do is I'm going to do the top equation, take away the second or the bottom equation. So I'm going to go minus, 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 and that's going to carry on, minus, minus, and minus, and minus. And hopefully you can see here what's going to happen is that this is going to cancel with this is going to cancel with this is going to cancel with this. All of the ones in the middle here are going to follow this same pattern, which means that when we get to the end here, everything here, so here all the way to here, is all going to cancel out. Which means that what we're left with is on this last line here, I'm going to do this in blue, Sn minus Rsn on the left hand side is equal to, well, the only thing we're left with is this, because a minus nothing is just a. And then on the other side, we've got this ar to the n, so a, and don't forget this is 0, so 0 minus ar to the n is just minus ar to the n. Remember, all these other ones are going to cancel out. So Sn minus Rsn is equal to a minus ar to the n here. We can factorise both sides. We're going to do that now. I'm going to factorise both sides to get Sn, we can take out here, is 1 minus r, is equal to, well, on the right hand side we can take out the a. So factorise using the a 1 minus r to the n. And then to get Sn on its own, it's being multiplied by 1 minus r, so I'm going to take that underneath. Sn is equal to a 1 minus r to the n all over 1 minus r, and we have proven what was asked. Just remember, guys, that r cannot be equal to 1. Okay, so we're just going to use that formula now. We'll just write that down again. So we said that S of n was equal to a 1 minus r to the n all over 1 minus r. And you can see it says find a formula for Sn for a geometric sequence 3 plus 3 over 2 plus blah 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 blah. So hopefully we can see if we have 3 plus 3 over 2 plus, and it tells us it's geometric. We can see here that the first one, our A, our first term, is equal to 3. And how do we get from 3 to 3 over 2? Well, you can see here we're multiplying by a half. So R is equal to a half. I don't have to prove it, boys, because what we have here is the fact that we are told it's a geometric sequence, which means that A and R are implicitly told that we can use the whole idea that this has a common ratio. And you can see here, to get from 3 to 3 over 2, what we need to do, we need to multiply by a half. If you're not sure, you could do T2 over T1, and if you did that, so R could also be T2 over T1, which would be 3 over 2 divided by 3, and again, if you do that, you're going to get a half. Okay, so there's two different ways to do it. Normally, you can just see it. There's no need to do this unless you can't actually see what your common ratio is. Okay, so we're just going to stick the numbers in. So our Sn now is equal to A1 minus R to the n all over 1 minus R. Just stick in the values. So A here is 3, and what we end up now is 1 minus a half to the power of n all over 1 minus a half. Tidy it up if you can, so we get 3. Okay, 1 minus 1 over 2 to the n over a half, and what we could do is 3 divided by a half here, so 3 divided by a half is 6. Okay, it's equal to 6. 1 minus a half to the n, and if you're going to be really pedantic, we could as well say that this is equal to 6. 1 minus 1 to the n, so we could break that up, say 1 to the n over 2 to the n. And 1 to the power of anything is just 1, so that means what we're going to end up then is we end up with 6, 1 minus, and it's going to be 1 over 2 to the n, and we are done. So that's our Sn. Okay, it then asks us, it says for part II, it says find the value of n if Sn, so Sn is equal to 381 over 64. Okay, so 381 over 64 is equal to, and we've got this down here, so we can put that equal to this to get 6, 1 minus 1 over 2 to the n. Okay, so the first thing we need to do is divide everything by 6, and if we do that, 381 over 64 divided by 6 turns out to be 127 over 128. And that leaves us just with that bracket, which is 1 minus 1 over 2 to the n. The next thing we're going to do is we'll take that 1 across. So we'll take the 1 across. So 127 over 128. And minus 1 means we're going to get minus 1 over 128 is equal to minus 1 over 2 to the n. Okay, next thing we'll do is we'll get rid of those negatives. So we've got 1 over 128 is equal to 1 over 2 to the n, and then we're going to cross multiply to get everything off the bottom. So remember to cross multiply, that's going to go up to here, that's going to go to there, so we end up with 2 to the n is equal to 128. Now we have our n is in a power, okay, so an exponent, an index, so in order to undo a power we need to take logs both sides, and we take the log by whatever base it is, so it's log base 2 to the n, and of course then we have to do it to the other side, so that's log base 2 of 128. If we do that, what we'll end up with, log base 2 will all disappear, so this, the reason we've done this is that this all cancels out, and we end up with n is equal to, stick log 2 128 in your calculator, and you'll get n is equal to 7. There's one other thing that we have to be able to do with geometric sequences, and that's a sum of infinity of a geometric sequence. And if A is the first term of a geometric series and R is its common ratio, then the sum to infinity is given by S to infinity is equal to A over 1 minus R if R lies between -1 and 1. So this proof is based on the S of n proof. So S of n is equal to a 1 minus r to the n all over 1 minus r. And there are essentially two types of geometric series, one that we call convergent and one which we call divergent. Now, a convergent one means that it goes to a particular number, a bit like a limit, where a divergent one means that it goes to either positive or negative infinity. So I'm going to give you an example of a divergent one. So I'm just going to put divergent, and if we take the just a very quick one here of 2, 4, 8, 16, and you can see here if I just label T1, T2, T3 and T4, you can see that T5, this isn't a difficult one to work out, we're just multiplying by 2 to get from each term to term. The next one's going to be 32, and it's going to get very, very big, very, very quick, because it's just going to keep increasing and increasing, increasing and increasing, and eventually that's going to go to positive infinity. As you can see here, that if 2 to the power of n, as n heads off to infinity, then you can see that it's just going to get bigger, bigger, bigger and bigger. So let's look at convergent sequence, okay? And if we have a look here, that we could have a half, a quarter, an eighth, a 16th, etc. Now, hopefully you can see that as if I added these ones up here, it's obvious 2 plus 4 plus 8 plus 16, it's all getting bigger, bigger and bigger, and it heads off towards that infinity. But if I have this one here, where my a is equal to a half, my r is equal to a half, so I'm multiplying by a half, multiplying by a half, multiply a half to get there, so my common ratio here. And you can see here that the common ratio is making everything smaller because it's between -1 and 1. Okay, so because it's between -1 and 1, what's happening is it's going to converge to a certain value. Now if I start adding these up, what's going to happen is if I have a half plus a quarter, that goes to 3/4. 3/4 plus an eighth, that goes to 7/8. And then we have 7/8 plus a 16th, which will then give me to 15/16, and so on and so forth. And hopefully you can see that this is converging to a value of 1. So this converging to a value is going towards 1. Now, the only reason this is converging rather than diverging is essentially based on r here. And if r is greater than 1, then you can see here, if I put, for example, 1 in here, we'll put it equal to 1 to start with. And I have 1 to the power of anything is just 1. It doesn't get bigger, it doesn't get smaller. Now, if I make r any bigger than 1, for example, 2, or even 1.1, what's going to happen is it's going to get bigger and bigger and bigger and bigger. If I have r less than 1, i.e. between 0 and 1, like here, what you can see is going to happen is it's going to converge to a certain value. Okay, and this is where we get the idea of it's going to collapse down into this. And it's all about the limit. So what we can say is S of n is equal to a 1 minus, and what we're going to do is we're going to take the limit, okay, as n heads towards infinity, of r to the n all over 1 minus r. Now, as we just said, or I've just shown you here, if r is greater than 1, okay, so if r is 1.1, 1.01 even, in this case 2, you can see we're multiplying by 2, multiplying by 2, multiplying by 2, what's going to happen is it's going to diverge. If it's less than 1, i.e. between 0 and 1, or to be more pedantic, between -1 and 1, what's going to happen is it's going to converge towards a certain value. Okay, now, as this gets bigger, so if we look at this particular one here, as we make n very, very large here, so if I say a half to the power of n, because this is my r, remember r is equal to a half, if I put that to the power of n, and I make that very, very large, so I'm going to take the lim, as n heads towards infinity, what's going to happen is this is going to get, as a half, that gets bigger, it's the same as 1 over 2 to the n, okay, I'm going to take the limit of that, and as n gets bigger and bigger, that means we're essentially sharing a pizza between more and more people. So you can see I've got 1 pizza, so when n is equal to 1, I've got 1 pizza between 2, when n is equal to 2, it's 1 between 4. If I make n into a million, So 2 to the power of a million is a very, very big number. So I've got 1 pizza divided by a huge amount of people to eat that pizza. If I take that limit, what's going to happen is I'm essentially going to end up with 0 pizza. So that means when I take this limit up here, I'm going to end up with this r to the n. It's going to come down as long as it's between -1 and 1, and that's the important thing. It's just going to reduce to 0. So I'm going to end up with my next line, s of n is equal to a 1 minus 0 all over 1 minus r, and s of n is equal to a by 1 over 1 minus r, and s of n is equal to a over 1 minus r, as shown there. Again, r has to lie between 1 and -1, and it cannot be equal to 1, and it cannot be equal to -1. So in this example, what we're going to do now is just go through a question that we might get asked in the Leibniz cert. So it says the sum of the first 2 terms of a geometric sequence is 9, and the sum to infinity of the sequence is 25. If the sequence has a positive common ratio, find the value of r and the third term of the sequence. Okay, so the first thing we need to do is write down what we know. So we know that t of n is equal to ar n minus 1, s of n is equal to, and it's going to be a 1 minus r to the n over 1 minus r, and the sum of infinity is equal to a over 1 minus r. We now have our 3 formulae. Again, remember those are in your tables books. Okay, so the sum of the first 2 terms is 9, so we know that s2 is equal to 9. That comes from here. The sum of the first 2 terms is equal to 9, and the sum of infinity is equal to 25. So we know that the sum of infinity is equal to 25. That means that we should be able to find out our a and our r, and then we can find the third term in the sequence. Okay, so s2, that means what we have here, so this first one here, we know that 9 is equal to a 1 minus r. We don't know what r is, but we know that n here is 2. Okay, so 2, and it's all over 1 minus r. Okay, so just to show you what's coming through here, so our n is equal to 2, so a 1 minus r squared all over 1 minus r. And we can get rid of the 1 minus r on the bottom, so we've got 9, 1 minus r is equal to a 1 minus r squared, and we can just leave it like that for now. Okay, so there's the first one. S infinity here, so it's the second one, is equal to 25, so we know that 25 is equal to a, which is just a over 1 minus r. And what we can do here is we can rearrange this and say that a is equal to 25 by 1 minus r. We can then rearrange this other one on the left here, so get this in terms of a as well. So we can say that this is a is equal to 9 1 minus r all over 1 minus r squared. And that now means that we have 2 equations that are both equal to a, and we can now put them equal to each other. So we've got 9 1 minus r over 1 minus r squared is equal to 25 1 minus r on the right hand side here. So look, this a is equal to this from this equation, a is equal to this from the second equation, so we can equate them, put them equal to each other, and that's what we're going to get in this one here now. There's 1 minus r here, 1 minus r here, so we can divide both sides by that, which now means we're going to end up with 9 over 1 minus r squared is equal to 25. And take the 1 minus r squared across, we get 9 is equal to 25 1 minus r squared. Go to here. We're then going to multiply that out to get 9 is equal to 25 minus 25 r squared, and take the 25 across. So 9 take away 25 will be minus 16 is equal to minus 25 r squared. Divide both sides by minus 25, which means we're going to end up with r squared is equal to 16 over 25. And take the square roots of both sides. R is going to be equal to 4/5. It's going to be plus or minus 4/5 because we're taking the square root, but we're told that it's going to be positive here, so that implies that r is going to be equal to 4/5. Need to find our a now, so we need to substitute into our a. So I'm going to substitute it into this one here. Okay, so I'm going to substitute 25 is equal to, so look, 25 is equal to a over 1 minus 4/5. So 25 is equal to a over 1/5. And if I multiply that across, I get a is equal to 5. So I now have my a and I now have my r. Term 3 then, just to finish this off, is equal to a r n minus 1. So let's put them through. So T3 is equal to a, which is 5, multiplied by r, which is 4/5, to the power of n minus 1, which is 2. You stick that into your calculator and you get T3 is equal to 16/5. And we're done.